is, I don't know how to read it, but x squared plus 2 and close parenthesis and over, what's that, power of 2, like 2 in the top, yeah, over x minus 5.
Okay, so what are we trying to do here?
Yeah, just give us like little example looks like this, because I don't want her to say like we're computing exactly what.
Right, but what
Just
is the
from the
question? What are we asked to do? We're asked to
find the horizontal asymptotes.
Yes, what else?
That's it, but we need to show our work.
Okay, so are you sure that this is x squared plus 2 squared?
Yes.
Are you
And
sure
there's
that
another one else, almost the same, that she put in the bottom part. The x squared plus 2 is in the bottom, the denominator. That's also the other question. So I'm just like confused how we gonna like solve that.
yes, I will show you the horizontal asymptotes, how we determine them, but can you verify that this is x squared plus 2 squared and the denominator has degree 1? Oh,
yeah.
Something happened here.
Yeah, that's exactly our problem.
So this is the degree 1, and this is, can anyone tell us what degree is this?
4.
Exactly, because it's x squared squared. Awesome. Perfect. No horizontal asymptotes. None. So a horizontal asymptote is found when degree n over degree n, same degree in other words, same degree over same degree, or degree n and degree greater than n. If the numerator has degree 4 and the denominator has degree 1, there is no possibility for a horizontal asymptote. Horizontal asymptotes, an example for this will be x plus 2 over x minus 3, same degree over same degree. Another example, x squared plus 4 divided by 3x squared plus 2, the same degree over same degree. An example here will be, for example, x over x cubed plus 1, degree n, and higher degree in the denominator. Another example will be x plus 1 over x squared minus 3. Such a problem with degree 4 at the top and degree 1 in the denominator does not have a horizontal asymptote. That's why I was asking, are you sure that this is the question?
Yes, ma'am.
So there is no work needed to be presented here, other than you have to say, just in writing, degree 4 over degree 1 does not have a horizontal asymptote, not even a slant asymptote. It will have a vertical asymptote because x minus 5 cannot be 0, so x cannot be 5, which means x equals 5 is the vertical asymptote. But a problem with degree 4 over degree 1 cannot have a horizontal asymptote. So these are the two possibilities for horizontal asymptotes. Same degree over same degree, degree 1, degree 1, degree 2, degree 2. It will always be the leading coefficient over the leading coefficient, 1 over 1, or 1 over 3. Or the second possibility for a horizontal asymptote, a smaller degree in the numerator than in the denominator. Degree 1, degree 3. Degree 1, degree 2. So I'm going to use a different color here. Y equals 1 is the horizontal asymptote for this one. 1 over 1. Here, 1 over 3. Y equals 1/3 is the horizontal asymptote. For both of them, for all these situations, y equals 0 is the horizontal asymptote. Anytime the degree in the numerator is smaller than the degree of the polynomial in the denominator, like here, 1 over 3, not leading coefficient, degree 1 over degree 3, horizontal asymptote 0. degree 1 over degree 2, horizontal asymptote 0. Such a situation does not have horizontal asymptotes. Was this the question? Did I answer what you're asking, or did I misunderstand?
Yeah, that's it. I'm just making sure that I don't need to calculate inside the parentheses. No wonder why I am confused.
Okay, so now is this clear, you think?
Yes, ma'am.
Perfect, awesome. So as I mentioned, I just want to write down here my cell phone. So it's 240-675-0445 in case you have questions about the lecture of today. And mmlead@aacc.edu in case you want the recording and these papers. I'll create a PDF file with all the papers we write today, all the notes we write today, and I can email them to you, including the video links. Let me just push my computer a little bit. Yeah, of course, I know, I saw that. It cut off the camera. Okay, good. Perfect question. Anything else? Do we have anything else that we want to go back to? Any problem? Anything? Anything? I hope it's not going to create a problem. Sometimes there's just a little glitch there. Okay. Anything else you need help with? Anyone? Okay. So in that case, let's continue with 4.2. We are talking about logarithmic functions. I saw that. Good. So first, let's review a little bit about exponentials. You probably know why these two functions are in the same chapter. And the reason is because they are inverses of each other. They are inverses of each other. The log function is the inverse of exponential. The exponential is the inverse of log. So last time we looked at 4.1, which deals with exponential functions, and we realized that there are two different shapes for the exponential function. Of course, because there are two different shapes for the exponential function, we are going to find two different shapes for the log function. So let me refresh our memory on these two shapes. Oops. Here is the first one, which you see is always increasing on all its domain, and its base, so it's a to the x, that's the exponential function, with a base greater than 1. If you want an example, I didn't think we would have to talk about it, but this is what we've been going through for the last 2.5 years, this pandemic. That's why you heard the CDC say, oh, maybe we can flatten the curve. Let's flatten the curve. Well, I guess we are there. We've been there for a while. So this is a scary function because the growth is so huge. Okay, so here's the other shape. The other shape is a decreasing function on all its domain. As you see, it's always decreasing. And this function is still a to the x, but the base is tiny. So it's between 0 and 1. Increasing on all its domain, decreasing on all its domain. Base greater than 1, base less than 1. Now, whenever in the past we graphed inverses in chapter 2, when we graphed inverses on the same coordinate system, the very first thing we need to do is graph the line y equals x. Y equals x, which is the line that bisects the first and the third quadrants, half, 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 half. So then y equals x. Although we haven't discussed anything about this function yet. We have no idea what it is, its domain, range. We haven't discussed anything about it. I can still graph it, although I don't know anything about it. But I know that it's the inverse of this function. So if this is increasing, when I overlap this graph with respect to y equals x, all I have to do is just reverse it. So here it is. It crosses here at 0, 1. It has to cross here at 1, 0. And I'm creating a mirror image of this graph with respect to y equals x. And here it is. So this is the graph of the inverse function of a to the x, right here. Notice that this function does not touch y equals x. So there is no common point, but this one has a common point. Here it is. Here's the common point of the exponential function with y equals x. All these points here have the same x and the same y. So this point becomes a point of the inverse as well. So here it is. Here is the graph of the inverse function of a to the x when the base is less than 1. What do you think these are? Of course, the graphs of the log functions. So this is the graph of the log function, symmetric with respect to y equals x of the exponential function, a to the x with a greater than 1. Same thing here. If you fold the graph with respect to y equals x, you will see this piece overlaps this one, and this piece overlaps this one. So I always like to present these together, even before we discuss domain and range for the log function, even and the special functions that I'm going to show you in a minute. Okay? So if you remember the graphs together, you will never forget them. Increasing, increasing. Decreasing, decreasing. And the common point on y equals x. There is no common point here on y equals x because the exponential does not touch the y equals x and the log will not touch. Good, moving on. Any questions? You want to stop me anytime if you have any questions, anything. Any questions? Okay, now so let's go back to the exponential function. Can anyone give us the domain of the exponential and then the range of the exponential? Can anyone tell us? What is the domain of the exponential function? Look at the graph and identify the domain. Yes, I saw that. Excellent. Negative infinity to infinity. Thank you. Perfect. Look at the graph now and give us the range. Awesome. Thank you, Sydney. Yes, Emily?
Negative infinity to positive infinity.
Careful, let's look at the range. Look at the red graph. And we identify the domain as being negative infinity to infinity. But now let's identify the range. Remember how we find the range? Imagine
1 to infinity?
Yes, it is 0. 0 with the open to infinity, right? Awesome. Thank you. Good. As we know from chapter 2, these inverses, two functions that are inverses of each other, one goes from negative infinity to infinity domain and range, but now the log function, which we don't know much yet. We know the graphs already, but we don't know more details yet. What will be the domain of log and what will be the range of log? So this is the domain and this will be the range. This is how we like to write it. Exponential function is defined on domain negative infinity to infinity, taking values, and the range 0 to infinity. Now, can anyone for the log function look at the graphs? So this is the graph of the log, and this is the graph of the log.
0 to infinity?
Exactly. This has to go here. Perfect. And about the range?
Negative infinity to infinity.
Exactly. So that's one of the reasons why we say they are inverses of each other. Domain range, domain range. Good. So keep that in mind by simply looking here. This basically rings a bell, I hope, or an alarm. What's the alarm? I like to call this function friendly. I don't have to worry about it. Its domain is all real numbers. I never have to worry about it. But this is a problem. I always have to remember that the log function, whatever form, whatever base, whatever it looks like, the log function has to be defined on positive values, not even 0. Okay? Do we know other functions that do not have domain all real numbers? Can anyone give us 2 examples, or at least one? Is there another function that has restrictions? On x or the variable? Have we encountered other situations in which we said, oh, gee, we have to look at the domain because this is not defined everywhere? Anyone wants to give an example?
X equals 3.
X equals 3 is not a function. We want a function. Can anyone give us a function that will also have restrictions on the variable or limitations? What about the square root of x minus 1? How would you write the condition or the restriction, if you want, for this function? What could go wrong here?